Hi, so today we're going to talk about problem set 4, solve it, hopefully. Okay, the first question was consider this game, find all the pure strategy Nash equilibria, then find the set of Nash equilibria that are trembling hand perfect, and show the working. So let's start by trying to find out all the pure strategy Nash equilibria of this game. We do what we always do, which is to find best responses. So if player 2 plays W, player 1's best response will be to play either T or V, because both give player 1 5. Player 2 plays X, player 1's best response is T. Player 2 plays Y. Any of these three are best responses, and V is the only best response to Z. If player 1 plays plays S, then player 2's best response is either X or Y. Player 1 plays T, player 2's best response is X. If player 1 plays U, player 2's best response is either W or X. And if player 1 plays V, then player 2's best response, oh sorry, this should be a 2, is Z. Okay, so our set of pure strategy Nash equilibria are SY, TX, UW, and VZ. Now we can rule out some of these Nash equilibria if we think about trembling hand perfection. So there's two ways of ruling them out. One is just to simply make the claim that in two players, trembling hand perfection rules out all weakly dominated actions from being played in equilibrium. The other way is to calculate the expected payoffs. If we just use the first way, which is to just simply say that in two-player games, trembling hand perfection rules out all weakly dominated actions from being played in equilibrium, then we can rule out, which ones? We can rule out U, because T weakly dominates U. You can see that here, right? Here they get the same payoff, here they get the same payoff, here they get the same payoff, T and U. But against X, T does strictly better than U. Therefore, T does at least as well as U against all actions played by player 2, except for X, where T does strictly better. Therefore, T weakly dominates U. So we should therefore be able to rule out U. It so happens that X also weakly dominates Y. It doesn't have to. In fact, we could have here, let's see, what could we have here against T? For instance, we could have this here. We could have Y not be weakly dominated by X and still be able to rule out this equilibrium UW, because U cannot be played in equilibrium because U is weakly dominated by T. Similarly, we're able to rule out S being played in equilibrium because S is also weakly dominated by T. And by ruling out S, we can rule out SY. And we just have to rule out one of the player's actions. We don't actually have to rule out both of them. It's neat that we can, but we don't have to. Okay, that's one way of doing this. Another way is to calculate out the expected payoffs by assuming that S is played with a probability P1, T with a probability P2, P3 for U, and P4 for V. Then Q1, Q2, Q3, and Q4 go up here. We can calculate the expected payoff from playing S. That would just be the expected utility for player 1 from playing S, and that equals 0 times Q1 plus 0 times Q2 plus 2 times Q3 plus 0 times Q4. can calculate for T, the expected payoff would be 5 times Q1 plus 3 times Q2 plus 2 times Q3. Yep, that's it. Oh, this is making sense. If it's not, ask me during the Zoom lectures. What I'm doing is I'm multiplying the payoff that player 2 would get from the outcome TW with the likelihood of W being played, so as to get the expected payoff from playing T, right? So you get TW, or you could get TX, or TY, or TZ, each with its own probabilities. For you, the expected payoff would be 5Q1 plus 2Q2 plus 2Q3, and for V it would be just simply 2 times Q4. Okay. Now for S as well as for U, we can see that T is going to give a strictly higher expected payoff, right? Because when there's a tremble, when we know that player 2, no matter what action he or she actually chooses to play in equilibrium, is going to make mistakes, then we know that Q1, Q3, Q2, Q4, they're all going to be positive numbers. If they're all going to be just positive numbers that add up to 1, then we can say that this, the expected payoff from playing T, will have to be strictly greater than the expected payoff from playing U, simply because Q1, Q2, Q3, they're all positive numbers. None of them are equal to 0. Same logic applies for S. And therefore we're able to rule out S and U from being played in equilibrium. And therefore we're able to rule out the equilibria SY and UW respectively. We could also do this exercise by looking at the expected payoffs that player 2 gets from playing these strategies W, X, Y, and Z in equilibrium. But again, like when we were ruling out weakly dominated strategies, we don't have to do that. Okay, so the trembling hand perfect equilibria are just Tx and Vz. We aren't able to rule out Vz because 1, it's not weakly dominated, and 2, I don't know if 2 times Q4 is going to be higher or lower than these numbers. All I know is that Q1 plus Q2 plus Q3 plus Q4 has to equal 1, and that each of them individually is positive. Okay, I'll see you in the next video.